Before moving forward and layering additional complexity on top of the system, I wanted to sort out a few nagging issues. And there were a few of them which I had identified as issues that were just me misinterpreting things. So I like those. But the one that ended up being a bit of a production, and you may have noticed, was that at the end of this first test sequence, and in other ones too, there's a weird blip on the second motor right at the end of the replay sequence. I couldn't find any obvious reasons for this error in the code right off the bat, so I serial printed all of them out right before they get sent to the motor. So this, because I know that the motor function works well, I've tested that a lot of times. So we printed those out, you can see that spike at the end, and then I dropped them into Excel here, and you can see that the change is the same between each one. There's a 2049 in there, that's just a rounding thing. So I know that the interpolation function is working fine. And I wanted to make sure that we were indeed on the last loop. So we have I just printed out last loop there. And I know I can see that it's coming up there and then going back down. And I could not figure out what was going on. So I even went into the code here because it seemed to be changing that last value in the array and had it set the thing to 0 and then serial print it right after that. And that indeed fixed it and made it 0, but it does not solve my overall problem. The way that I'm storing these numbers is in an array. And an array, if you're not familiar, is just a variable with multiple positions in it. There may be a different computer science definition, but basically you can just store a lot of variables in one big variable, and it makes it more convenient rather than having position 1, position 2, position 3. You can have position and index through it. And so these indexes go from, it's 10 spaces big, but they go from 0 to 9 in this example. And then you can fill each of those spaces with a number. So these are our rate values. And then you can make them 2-dimensional or more. So in here we have across the bottom 0 to 9, and then above 0 to 1. This is a 2-dimensional array, and they can be much bigger. So if you want to define it though, it's 10 by 2, but the index values go from 0 to 9. So if we want to know what position 6-1 is, we get 265 back because that's the value that's in there, and then we could assign it whatever we wanted to. So my problem is with this last spot in the array, the very last one. And the reason why there was a problem was that if you look at my code and you come in here, you can see that I'm using 1 and 2 because it's motor 1 and 2, but it's position 0 and 1. So I was actually out of the array up here in Fantasyland. And the thing that made this so difficult to catch was that it worked fine for all of the previous positions. And I'm sure there's a good explanation why that last one was changing randomly, it wasn't random. It would do exactly the same thing each time, but it had nothing to do with what I was telling it to do, or at least a direct relationship. So it worked fine for all of those, and it was only the last one that was the problem. So that was really throwing me for a loop because everything is working fine, except for that one spot. Anyway, I finally narrowed it down. It took a ridiculously long time, but this just confirms that tunnel vision is real. I was so focused on not screwing up the 0 to 9 thing. I had it in my mind on the first set, the up to 10, that I completely ignored it on the second one. So there you go, but we got it sorted out, and now we're ready to move forward. We have no other nagging issues, and we can start putting some improvements in place. I wanted to experiment with PID control, and a PID control is pretty simple. It's proportional integral derivative. And what that means is that you adjust your output rate based on 3 things: the current error, the cumulative error, and the rate of change. And then you adjust each one of these contribution to how much you output. So what I've done is I've disconnected the motor from the bottom main arm and left it on the top arm. And what I'm trying to do is keep that top arm level even if I change the angle of the lower arm. Our first test is proportional only, and the gain is set way too high. If you crank the gain down too much though, it'll be much more stable, but it'll take a long time to reach that equilibrium point that you want. By adding in the I and D components of the PID and then adjusting their gains, you can get much better overall performance. Add in too much though, and it'll cause your performance to go right back down. I ultimately settled on some pretty good PID settings, but it didn't seem that necessary overall because in practice I'd be using this fairly slowly, and I haven't really had an issue in those cases. And it does cause a bit of a settling problem, which I was having difficulty with on this machine. I think part of it is that the upper arm has a very high tendency to rock back and forth. It has a lot of inertia, and the stepper motor, even when I cranked up the frequency so that it wasn't stepping as far, it puts inputs in a step function. So it's a step and a step. And so even if you step forward and it overshoots and you step back, like it didn't seem to be working. And then the belt adds some flexibility there. So I either need to put a lot more effort into fine tuning these coefficients or adjust my system or just learn about it more in general, because at the moment it worked okay, but was not ideal at all. The simple solution really seemed to be working the best, so I'm going to stick with that for the time being. The next major improvement idea was to smooth out the motor outputs. So we have a graph here of our rate and time of the motor. This is straight from the encoders that we've computed. Put a couple dots on there for our data points. These are actually step functions, meaning they jump to a value and then stay there. But I'd already made these graphs by the time I realized that, so we're going to stick with line graphs for now. So we've gone ahead and connected those lines together. And the parts that we want to focus on are these sharp changes, because that's where the motor's going in one direction, and then, either in one direction and changes direction like these are, or just changes rate very rapidly, and that's where you get that tone sound from the motor changing. So if we want to reduce that top peak, what we need to do is start in this area ahead of it, and if we interpolate linearly, which is what we're showing here, it only depends on that point and at the beginning point and the end point for that range. So what we need to do is look at the slope of the section before and after where those arrows are pointing to it. So if we go ahead and average these out by, say, 5 periods, which is about halfway into each one, you can see that it really smooths out those rapid changes. But the thing that we have to be careful with smoothing these out is that going at a rate over a time creates a distance. So at the top there, we're not going to go quite as far in one direction. At the bottom, we're going to go a little bit less far on the way back. So they need to average out over time roughly, but we do need to be careful of that because you can end up in a different spot at the end than when you were recording it. I did a little experimentation with the numbers in Excel just to make sure that the smoothing wasn't going to be too extreme or not extreme enough. And it looked like the 7 period was actually going to work the best, so that's what I'm using in practice. These are some actual numbers that came out of the Arduino, and here you can see that step function also quite a bit better. But it looks like exactly what we want. We have the blue being our sort of unprocessed output, and then the red being the smooth one. This is 7 periods, and it does a pretty good job, so let's see it in real life. I was going to show a comparison shot of the unprocessed output replay like we had before running and then the new one, but honestly they don't look that much different. Even standing there in real life, listening carefully, and then watching the replay immediately afterwards, I couldn't really tell much of a difference. So, except for the fact that when we smooth it out, it does end up in a slightly different position at the end, depending on how much high-speed travel you had that was averaged out. So it really didn't seem like it helped that much, and it added quite a bit of complexity. It took a bit more memory on the software. I was able to, a slight amount of cleverness to keep from having a massive array in there, but it still took more effort, and it didn't really seem to help. So I'm actually going to leave that out too, sticking with simplicity. I started cleaning up the ends of the connectors on the encoders and the motors and some other things because I'd alternately been soldering them with too much heat and simply jamming them in the breadboard after tinning the ends, neither of which was ideal. And I know someone recommended a better solder technique, but I haven't given that a shot yet. The thing with crimp connections too is they're all closed up. They're inside the connection. It's very neat and tidy. Even if I soldered them, they have the risk of bumping into other things. So I'm going with the crimp connectors for now. Gives it a nice clean look and spaces them out so they sit on the header pins. With the test mechanism working pretty well, I've started thinking about the next version, which should have full functionality. And in order to pan and tilt the camera and manipulate some things up high, I went ahead and ordered one of these Dynamixel digital servos. The regular analog servos jitter too much, and they don't have Some of them have continuous rotation, but it seemed like these had the full package. I mean, they have continuous rotation if you want it. They're digital, position feedback. They can give you other things as well. They can be daisy chained. So order one of those. We'll give it a test drive. They're also pretty light, which would be a major advantage over the stepper motors for things that are further out, because you end up multiplying the mass by the time you get back to the final counterweight by 4 or 5. And I've also started thinking about what the final one's going to look like. I was originally quite enthusiastic about having 360-degree rotation on the arms, because I felt like that would give me quite an advantage, or at least it would look cool. And then I realized that it would look cool, but that's it, and it wouldn't be much of an advantage. As long as that base can rotate, you can do almost everything that I was hoping to do with the continuous rotation. And if we take out the continuous rotation on those arms, it'll make the mechanism a lot simpler. They won't have to be cantilevered out like they are in this animation, which will make the mechanics of it simpler to make. So I think we're going to skip that for now, and make it a bit simpler. So these things are taking a little while to come in the mail, and in the meantime, I've acquired some additional parts for a project to fill the time in between. So you can look forward to a bit more of that next week. That's it for now. Thank you for watching.